Thank you very much for coming. Can you hear me? Where?
We can.
Am I delayed?
You aren't for me.
I don't
so.
think you're delayed. We can see your screen, the green screen.
Okay, good. And we would like to thank Scott for moderating and doing so much computer work. This is put on by the IEEE EMC Southeastern Michigan Society. So thanks for coming. I just want to go over the basics. I get to do the beginning. These are great books on EMC. And of course, the signals is a big part of what we do. And you'll hear me talking about, oh, let me turn off my, maybe if, let me, how do I do this? Just a second.
No.
It's not doing anything at the bottom, sorry.
Zoom. Where's your Zoom?
Zoom is over here. Sorry, we're so, okay.
Yeah,
So I'm gonna
your
stop
video.
my video. We'll get
Maybe
this.
that'll work better.
Okay. Beginning. It's not doing it. Okay, now try it again. Sorry, there was too much of a delay. Anyway, these are great articles and they'll give you some background. Why do we care? Well, pilots really care because you can trigger the fuse. I want you to understand why I care about electromagnetic compatibility. The basic ways people measure EMC, the key elements, and why it's important for everyone. Okay, what makes up EMC? This is what you should take away. There's two parts to it. There's narrowband, broadband. I want you to be able to tell me two types of broadband noise, three types of narrowband modulation, and why 60 hertz switching of a light makes noise at 1 megahertz and interferes with my AM radio. Why does a cell phone operating at a gigahertz frequency make an audio frequencies noise in a speaker? Common and differential mode, what is that? Easy ways to get rid of conducted problems, radiated problems, and 3 different ways to measure or induce electromagnetic noise. What is it? It means that electrical devices don't interfere with other equipment or themselves and are not affected by other devices. My two sides, we have emissions. So there's conducted and there's radiated. Immunity, my oven
reputation was sealed. It's one of the most famous
hit by
kings.
it was not immune. That was the problem. And who is driving this? Well, governments care, people who fly, people who drive, people who listen to the radio, hospitals. Every time I see a harness, I just think antennas. And lawyers who make their money, oh, they care a lot about EMC. What causes the problems? Wires. Every wire and many things that aren't wires, such as a optical cable with a Metallic coating, it's a wire, it's an antenna. Electronic and mechanical switches, oh. The arc, the direct delta, that'll get you. Circuit board, IC design. Every time you see a loop, you think antenna. Cycle rate of software. You can actually find out what people are doing just by looking at the software. And let us not forget 70s shag carpet. So the topics in school, what are you going to look at? Electromagnetics, signal processing, communications, analog electronics, digital electronics, and PCB layout and software. So electromagnetics, we think of antennas. Signal processing, think of receivers. Electronics, the filters, and all those wonderful cell phones. The kind of tests that we do are radiated emissions, conducted transients. We also look at whether a device is immune to radiated noise, conducted noise, and ESD. So with examples of ways we take care of these things, when we have transient emissions from a blender that are causing problems with other computers, we unplug it. If I'm running a blender while watching TV and it's not a cable, then I can unplug it. The blender also, because it's a broadband noise, will cause problems with radios, especially AM radios. If I place a speaker next to my computer monitor and there's not shielding, I can see issues.
No.
During a computer storm, you should unplug your computer. And just like that, there's smaller events that can cause problems in power. When we think of radiated immunity, you can think of, oh, you know, I shouldn't place my iPhone in the microwave. That'll get you. Current injection and coupling. Do not put a network cable next to a HVAC unit because the thing will cause noise and you want to be able to get any information on your network cable. Has anyone ever watched the ESD videos on their site? You really need to stay outside your car while refueling, especially if you're wearing polyester. These are measurement facilities. You can think of a reverberation chamber as a microwave oven. You've got all these frequencies and they impinge on your device under test. Or your device under test sends them out. So reverberation chamber will sort of concentrate it and hit it with a lot of different frequencies. It also can shield it, like the MRI, the reverberation chamber that the MRI is in. The next thing that we have is semi-anechoic and anechoic chambers. These are best if you start in a reverberation chamber and then you move to semi-anechoic or anechoic chamber. And you can exactly figure out what polarization and frequency that you're looking at and where the problem is. The kind of equipment we use: probes and antennas, EMI receivers and spectrum analyzers, artificial networks, oscilloscopes, transient generators, ESP rings, power amps, and of course, the most important, standards and procedures to make sure that everything we do is the same. This just gives an idea of where we have different antennas, you know, AM radio, kilohertz, FM radio, megahertz, and cell phones, gigahertz. That's not exactly right, but it's close. So we live in the time domain. Everything we do happens as a function of time. When we're looking at a device under test, we can look how the time domain intersects with the frequency domain, showing the relative occurrence of repetitive portions of the signal. A continuous signal, you can think of a signal generator, 60 hertz power lines. Modulated signals, all radio, TV, and communications transmissions are modulated. Cell phones, radar, digital signals. There's transient signals. Those are exciting. Electrostatic discharge is transient. So is switching. And of course, one of my favorites, the thermal noise from the universe, which we listen to find out if somebody else is out there.
Excuse
And
me, can we please have, there's a few microphones open. Please mute your microphones so the speaker's not interrupted. Thank you.
okay. Examples of broadband noise: DC motors, switching circuits, mechanical relays, thermal noise. Any sort of circuit or relay causes arcs, and so do DC motors. Narrowband noise, we can think of a radio station, communications, microprocessor clocks. And we have to remember that narrowband and broadband are determined by your bandwidth. So the kind of terminology I use: resolution bandwidth, video bandwidth, dynamic range, attenuation, reference level, preamp, preselector. By the way, you need one. Impulse response, time domain scan, FFT, and CISPR16. Why do I use decibels? I use decibels because I can tell you something small and big at the same time. It's a great way. For example, 1 volt is 120 dB microvolts. 1 watt is 30 dBm. Now, the reason why it's different, one is multiplied by 20, another is multiplied 10, is because power is V squared over R. And that's 20. And of course, watts are power. We have coherent broadband noise. It's made up of noise spikes that are regularly spaced. So signal strength may be constant, and the amplitude may increase linearly with the bandwidth. Incoherent broadband noise, they're random. Think of thermal noise from the universe, not as regularly spaced. Now, bandwidth is not a measure of the waist size of the percussion section. It's the frequency width of a filter. So the filter is a funnel which accumulates signals within the bandwidth and spits them out as a single value. Bandwidth is not always the same. You can have a 3D bandwidth or a 6D bandwidth, and it's going to give you a different result. So how do we modulate our narrowband signals? One way is continuous wave. Communication signals may be attached to a signal of one frequency called the carrier frequency. And of course, Hedy-Lamar's spread spectrum, which is great. Communication signals, AM. So you have the carrier wave, and you'll see higher and lower values of the carrier wave. Why? Well, that changes the information. And then I get the information based on the amplitude. That is a really noisy signal because it picks up so much noise from the universe. Frequency modulation. Then I have my carrier wave, and I subtract or add to get my information. Pulse modulation turns the carrier on and off according to a digital signal. Here's some narrowband signals. And here might be a radio station. It's got sidebands. Narrowband noise. The big thing is switching. Oh my goodness, switching. Anytime you have a sharper edge, it's going to take more to add up to get that sharp edge. It's not like a sine wave. You've got more information. And so that's a real problem. Here's our square wave. You can see the fundamental and the harmonics. And harmonics from a signal produce noise at higher frequencies. Pulse modulation. Pulse modulation is a lot of fun because you can actually get lower frequencies, because things like a speaker will read the outside envelope of a pulse, like a cell phone, which is why they're shielded. Sine waves, we love sine wave. Exponential decay. This causes our harmonic. So signals, oh, how do I get, if I'm doing the laundry over here, how do I wake up a computer that's 20, 30 feet away? Radiation. We have conduction. There's ESD and transients that cause us excitement. There's capacitive coupling, think of plates, inductive coupling, transformers, and of course radiation. And here's some pictures. Magnetic coupling, think of loops on your circuit board. Electric coupling, think of layers on your circuit board. And wires, anything metallic will radiate. Differential mode currents are good, especially when they're close together and twisted. That's very good. Common mode currents, we don't like. They're also called antenna mode currents, and they radiate. A device under test plus wiring will act like an antenna because of the common mode currents. So hopefully you learned the two sides of EMC, emissions and immunity. The difference between narrowband and broadband. Broadband noise might be constant over large frequency. Narrowband is at one frequency. The two types of broadband noise, coherent and incoherent. Three types of narrowband modulation, AM, FM, pulse. Hopefully you understand how a 60 hertz light switching makes noise at 1 megahertz. How a cell phone operating at gigahertz makes an audio frequency noise in a speaker. The difference between common and differential mode. Common mode is the antenna mode, same current on both wires. Differential is the opposite current on both wires. Conducted problems, we can reduce the differential mode. Radiated problems, we reduce the common mode. 3 ways to measure or introduce electromagnetic noise. We have direct conduction,
Developed by language specialists teaching Spanish, French, and more.
capacitive coupling, and radiation. Okay. And now I'm going to turn it over to John. Are you going to?
Can you switch it so I can get the screen? Can you turn off your screen,
I will do that.
your screen share?
Stop sharing. Okay, I stopped.
Okay.
Candace, can you make me a co-host too, and I'll try to mute some of these folks?
Okay, that's good.
Do you know how to do that?
No, I don't.
You go to the participants list.
Oh, God bless you. Okay, so is that view?
It would be by the bottom. There's a button that says chat and a button that says participants. Next to where it said share screen.
Because I quit sharing my screen.
That's right. But down at the bottom where it has all those menu items, one of them says participants.
Okay. So,
And it will give you a whole list of everyone who's on the call.
okay, so I can go through and mute people.
Well, when you go to Scott's name, there'll be something that says like more. And if you click on that, one of the options will say make co-host.
Okay. We'll do that.
Then I'll mute folks if we're having any issues.
There's Scott, right there, more. Right. It keeps on disappearing. More. Okay. Make host. Right there, make host. Okay. You are the host again.
And you can add co-host, Scott.
Okay. Because I didn't have an option to make a co-host.
So Scott's a host.
Yes, Scott is the host.
So now Scott has to allow me to have screen share.
Okay, Scott.
Scott. We lost Scott. Wonder where he went.
Oh, I didn't push my space bar to talk.
Okay. Can you allow me sharing?
I think I just made you host, didn't I?
I don't think so.
Oh,
I
gotta
can't
push-
share.
I gotta push yes.
Scott, there might be a security button, and if you click on that, all right, never mind. It'll work now.
I can do it now.
Oh, thank you so much.
Okay, and I'm gonna go back up to where I start here. Yeah, I should have had it picked. I don't know why I didn't. Okay, and I'll just go here. All right, you should see my presentation, right? Okay. All right, so I'm going to review some of the things that we do to fix EMC and some problems that we've seen before that kind of illustrate the different aspects of EMC and things we did to study them and to mitigate the EMC problems, or at least understand them better. So here's what you should learn from this section. What are two methods to reduce radiated emissions? Why do we care if a DC signal is produced in an electronic circuit? What are two ways electrostatic discharge affects electronics? Two ways that noise can be introduced into circuits. How does a radio transmitter make signals? Ooh, this is a similar question to we had before, but hopefully you pick it up. How does a radio transmitter making signals at hundreds of megahertz make DC signal in an electronic circuit? And what is the basic electronic structure that leads to EMC problems? And what limits the effectiveness of capacitors and inductors? Hopefully we get that far. And three ways to influence EMC of electronic circuits. I'll try to go as long as I can before we move to the next person. Hopefully we can roll through this. So what are the different ways to mitigate emissions, electromagnetic emissions? One way is to add filters, and filters are usually comprised of inductors, which we call chokes, capacitors, or resistors. And there's different ways to implement those and construct those, and sometimes they can even be made inherent to device. That you can add shielding. That's simply conductive surface that's around or adjacent to a noise source or between the noise source and the receiver of the noise, and allows the noise to be blocked or blocks the noise from the emission source. We can add transient suppression for transient type noise. Those usually are comprised of varistors, which are they're not semiconductor devices. They are zinc oxide resistive devices. Rectifier diodes or Zener diodes, these are semiconductor devices, typically known as transorbs or TVS devices. You can also add RF absorber material. That's the type of thing that you'd find on a B-2 bomber. It's not something we typically coat our enclosures with, but I guess it could be done. I'm not sure how effective it would be for what we're dealing with. One example of a really bad noise source is a dimmer switch, which for a long time were used in our houses until they came up with the swirly bulbs. And now they're back again because we use LED bulbs. So I think they're still around. We still have ours and we use LEDs with them. So unfortunately, they make a lot of switching noise because they're comprised of a semiconductor switch, a thyristor, which is an older type of switching device. And it's set to trigger in synchronism with the AC mains voltage. And so by adjusting the resistor on the device, you can change the amount of the AC voltage and hence the AC current that goes from the mains to the light bulb. And when it switches, it makes a really fast transition. And so you get a high frequency noise at each of these transitions that are on here. And they occur at 60 hertz intervals. So you get a 60 hertz fundamental, but then you get harmonics that go way out, can be into megahertz range. And so if you hear it on a radio, for example, you'll hear a 60 hertz repetition at whatever frequency you're listening to. And it'll sound like a buzzing noise on your radio. So in these devices, if you take one apart, you'll typically see an inductor and a couple of capacitors, and these form some low-pass filters to prevent the switching or reduce the amount of switching noise that would get out onto the mains or through the wiring to the house. A low-pass filter, single-pole low-pass filter is comprised of an inductor and a capacitor, in a configuration like this. So if your input is on the right, the inductor tends to block the current going through, and then the capacitor tends to reduce the voltage at the output. So you get this reduced signal on the output, which it gets smaller and smaller as the frequency goes higher and higher because of the characteristics that you get from an inductor and a capacitor. The inductor gets higher impedance as the frequency goes up, and the capacitor gets lower impedance as the frequency goes up. And those work together to reduce the signal more and more as the frequency gets higher. So a type of filter that we're talking about may not work very well, say at the low end of the AM band, but by the time you get to the high end of the AM band, the devices that they use in there work pretty well, and you can't hear the noise anymore. So if you look at the way it's implemented on that device, it's got this inductor with a capacitor across the switch. This is a representation of the thyristor switching back and forth on and off. And so basically what you end up with is filtering across the switch, which reduces the sharp edge of the current going to the light bulb. So in order to look at it and study it, you can use some different devices. One thing we tried to do is use a current probe, and to do that, instead of buying one, we made some. If you can get some ferrite cores and have them cut, or cut them yourself, you can make a current clamp pretty easily with a piece of wire, and it doesn't have any shielding on the outside, but it's basically a ferrite ring with a wire wrapped around it. So it actually is like a transformer, and that can be hooked up to something that you can use to measure with. I'll use an oscilloscope here in a second, show you some plots. And if you add shielding on the outside, and we used candlesticks, brass candlesticks soldered together, the shielding makes it better because you don't pick up noise that's induced right on the wires. So this is a similar probe to what's given in CISPR 16, but you can make a pretty decent one that you can use for looking at things yourself. These are pictures of making one of the ones we had. So it was kind of a lot of fun to do this. We like to take stupid things and make them into something useful. If you hook that to a oscilloscope, you can see the noise under different conditions. So on the left, I have off, where the switch is off, and all we're getting is background ambient noise. And then on the right is with the dimmer switch on. So we talked before about common mode current. So if you clamp the probe around all the wires going to the light bulb, then you get common mode current. It's current that's on all the wires at the same time in the same direction. And you get some signal which repeats at 60 hertz, you see. So there is some common mode current going between the light bulb and the dimmer switch. If you then separate the wires and clamp the current probe only on one of the wires, you'll get differential mode current. That's current that comes through the one wire and back on the other one. And it's the way that, since it's the way the system works, the light bulb is lit up, you actually have a lot more current in differential mode than you would get in common mode. But the strange thing is this higher current for radiation purposes usually doesn't make as much noise as the common mode current, because you have current going one direction and right next to it a wire with current going the other direction, and the fields from those two wires generally cancel themselves out mostly as you get farther and farther away from the wiring. The common mode current, on the other hand, is, since it's always the same direction in all the wires, it acts in the same way an antenna works, and that's why it's called antenna current. And it can really produce a lot more radiated emissions per microamp. So how then do we improve immunity? Immunity, as we mentioned, is the susceptibility of a device to being affected by emissions from something else. Well, it turns out that the types of things that we do to improve immunity of a device are the same as what we would do for emissions of a device. We use the same capacitors, inductors, resistors, shielding, transient suppression, and RF absorbing material. They work the same way in reciprocity principles that apply to so that we know if we do one thing, it also works for immunity in the same way. Another way to improve immunity is to go digital. So implementing a digital stream of data allows you to check the data to, if you can detect it in the midst of noise, whatever that noise is, you can maintain your signal, and it can be very clear because it's undisturbed once you decode it, as long as you have enough signal to noise ratio to do that. So we have a very interesting immunity issue that includes a lot of different aspects of EMC. This was alluded to earlier by Candace. It's happened with our dryer, and we were doing laundry, and we kept having, whenever we were drying things with lots of static electricity, like flannel or whatever, the computer 10 feet away in the room, when pulling things out of the dryer, would suddenly wake up from sleep. And it was very strange because we weren't anywhere near it and couldn't figure out what it was. We finally convinced ourselves it had to be some sort of ESD related to the laundry. It was very odd. So in order to test that, we again made our own equipment. So we made a ESD gun. Some of you may have seen ESD guns and in labs or whatever. And basically they include a capacitor and some way to charge it and some way to discharge it. And you can you generate a high voltage, put it on a capacitor, and discharge it through the tip of the gun. And we made charging for the gun using transients from a switch. So we pump the switch a few times and generate a high transient from the switch, and that charges a capacitor, and we use that, then discharge that to whatever we're doing. Okay. And if you, the keyboard, we did a lot of study on this, trying to figure out what it was. Is it the mouse? Is it the monitor or whatever, you know? And we found it, that narrowed it down to the keyboard, because you start unplugging things and soon you find out, yes, it's the keyboard that's the cause. So we kept zapping near things until we found what was the, the most susceptible. And the keyboard was a USB keyboard. And normally what you do to wake up is hit a key, right? And so we looked at the USB on normal wake up, and what you get is this turn on kind of activity, and where it goes, the keyboard makes a constant voltage, and then the computer starts to wake up and communicate. And what was happening here was, when we had an ESD event, which you can see at the bottom here, there was a transient on the USB cable. And actually, I should say it's not, I don't think the keyboard that makes this signal, the computer makes this signal. So the computer's looking on the USB and sees this transient. If the transient is big enough and long enough, it thinks somebody has hit a key. It doesn't have enough filtering on the USB. And once it sees that, then it wakes up. And I think, let me just go to my folder here. The video works. Normally these demonstrations, when you do them live, don't work. So I'm hoping the video works. Okay, here comes the gun. Pump it, and you should be able to see an arc. And then it's talking and wakes up. We tried this with different computers. Some wake up, some don't. It's very interesting. There are certain models which are much more susceptible. Certain actual hardware setup or something. There's a difference, and some of them won't wake. Let me just play it one more time. It's kind of spooky when you see this. If you're not anywhere near your computer, you're not touching anything, and you get that arc, all of a sudden it wakes up. It's really weird. Of course, now they're waking up because of Microsoft, and you don't need the ESD. So that's also kind of spooky at 3 in the morning to have your computer turn on and try to do an update. Okay, so I'll go back to this. In tracing it back to what the cause was, we took the keyboard apart, and if you look in a keyboard, they're very interesting. They're layers of plastic with traces on them, and the layers, if you look at those traces, they form loops, and you can trace out loops, closed loops in these things, so that if there's a radiation coming, you can get a voltage induced in these loops, which ends up putting a signal onto the lines of the keyboard. There's different ways we get this signal. One is through those loops. Another way, there's a common mode path from the keyboard through the cable. And so you have to deal with both of these problems in order to fix this. So in order to fix the loop, the induced noise in the loop, which generates a current that causes it to wake up, you have to shield the keyboard. And in order to fix the common mode noise that gets induced on the harness, or not the harness, I should say the USB cable, you have to put something on the cable, some impedance like a bead. And that we did. And in fact, you can see a little bit of this if we take the current probe and used it to measure the transient voltage. There's a peak value somewhere here, I don't know, 1.5 volts. And then if you put foil on it, it maybe comes down a little bit. And then if you put the bead and the foil, it comes way down. And the best solution was the keyboard with the foil and the bead. And we did some tests at different distances, and how many clicks we have to put on the gun, which determined how high the voltage was. And the best was greater, 12 to 15 inches. Yes. You had to get within 3 inches to trigger it if you had the bead and the foil on it. But if you didn't have any of those things, then you could trigger it from 12 to 15 inches away with the gun. So, and of course, 10 feet with a flannel sheet. Okay. Another strange problem that we had was with our cell phone. And I have another video of that, so I will show that before I talk about it. And let's see, where is that? Let's try this one here. Okay. So there's the phone ringing. And now turn off the phone. And the phone starts communicating back to the network. And as it's communicating, it makes noise on those speakers. So that's audible noise on the speakers from the cell phone while it's communicating at some gigahertz frequency. So it's really kind of crazy. I'm like, how does this happen? So I play it again. It's an old GSM thing. There it goes again. And sometimes it was so bad, it was doing this from across the room. So really strange. And you wouldn't know what it was, except, if you had your phone next to it, you could figure it out. So turns out with this, the phone uses pulse modulation. So it has this signal that repeats at, it has a very high frequency signal, but it repeats at a very low frequency. And what that does is induces some sort of waveform, like I show on the right at the bottom, onto into the speaker somehow, and that's what you're hearing is that low frequency repetition, and all the high frequency stuff that doesn't get, I mean, that disappears in the process of putting the noise into the speaker, so it's rectified and you get this low frequency. Oh, I'm sorry, I will turn it back on. There it is. So here's a representation. You know, the phone makes this noise because it does something inside the amplifier of the speaker. And the frequency inside each of these packets is like 1.9 gigahertz, but the packets repeat at some audio frequency, kilohertz. So if you look at the output of the amplifier during the call, or when it's making that noise, before you get nothing, nothing, nothing. And as soon as it starts making the noise, you get some noise on the speaker amplifier. And if you just take a walkie-talkie and key it on, the amplifier responds to that too. But you don't hear that because it's like a constant signal. So it's a DC, but it's not a something you can hear through the speaker. However, that illustrates a problem because now I've taken something which is a high frequency noise and I've turned it into a DC level. And DC levels are what we use to do everything, trigger relays, trigger events like the ejection seat problem or airbags or whatever. So what causes that? Well, what causes that are diodes or and PN junctions in the circuit. So a PN junction will allow the current to flow only one way and not the other. And so if you have an AC signal, whatever the frequency is, the junction will rectify it and you'll end up with a DC level in current, or if there's a loop or voltage. And of course, PN junctions are in bipolar transistors. And you can get these, you can see that if you chain them together like you would in a Darlington kind of a circuit, you get this chain of PN junctions where current can flow. Some connections wouldn't allow that if you have two NPN and a PNP together. You have to really look and see the circuit to figure out where the current can flow. And usually, besides diodes, transistors, like as I said, bipolar transistors are likely to be places where that current will be rectified. And if you examine, for example, the circuit of that particular amplifier, it's an IC, and the input amplification circuit, it has these NPN transistors, and there is a path where current can flow through those, but you have to know what's out here on the rest of the circuit, where the path would be, to know kind of how to deal with it. So what we did was we made a simple demo to illustrate the principle here and how you might deal with it on a circuit. Although if it's in an IC, there's only so much you can do. So let me just show that real quick here. I know I'm running out of time, but I will try to be quick here. Okay, so first of all, if I have, I'll just take this one, for example. I made this circuit big so you could see it. And I have a walkie-talkie. It's a strange one, but when I key it on, you can see there's a diode connected between the base and the emitter of this transistor. And I'll keep playing that. There we go. And when you key on the thing, it on the radio, it produces a current in that part of the circuit, which then is used to turn on the it will turn on the transistor, which allows current to flow into this other LED over here. So I'm using the walkie-talkie with the right side of the circuit to bias it, and that turns on the left side of the circuit, the LED. So that shows you that I can produce C voltage in the transistor, on the transistor, which turns it on, and that in effect can be leveraged to do something much more noticeable, in this case an LED. There's another there are other things you can do with that, of course. If you can make a DC voltage to turn on a diode, you can do a lot of other things too. Here I'm going to key it on. See, so you can you can affect a lot of things with that, which is kind of scary when you think about it. That's why we have so many rules about handy talkie transmissions or whatever we call them. Okay. Yes, we have just a few minutes left. So I have a whole section on real world effects, but it's a little bit long to talk about in just a few minutes, but I'll just make mention that we use capacitors and inductors a lot in the filtering, and I mentioned the characteristics of inductors. The impedance increases with frequency and a capacitor decreases with frequency, and we use those together in a filter. I mentioned that earlier. Well, turns out that an inductor is only an inductor up to a certain frequency, and then what we call parasitic effects take over. Those are capacitance across the turns of the inductor that are always naturally there. It becomes then an important part of the impedance of the inductor, and you'll end up the impedance coming down after that frequency. And a similar thing happens with a capacitor. It has leads and that has inductance, which fights against the natural capacitance of the capacitor. So both of these are only having their natural or expected characteristics up to a certain frequency. Capacitor drops in impedance only up to a certain resonant frequency, at which time its parasitic inductance takes over, and an inductor only has an impedance increase up to a certain resonant frequency, at which time its parasitic capacitance takes over. And these effects you really have to be aware of when you're doing filter design. It's very important because the components you use are only good up to usually not up to very high frequencies. So you have to do other things to fix your problems. And we go into a lot of information about those things, but I'll just go over the elements of this section so we can review. So what are the two ways to reduce radiated emissions? Shielding and filters. We saw that early on with the keyboard. Why do we care if DC signal is produced in an electronic circuit? Many circuits use DC signals to accomplish their task. You saw a couple of those. What are two ways electrostatic discharge can affect electronics? Well, normally you think of them blowing up a circuit, destroying a component, but also the radiated noise from them can cause them to act improperly. And we call that indirect ESD.
Go on doing this, making knobs out of it.
What are two ways that electromagnetic noise can be introduced into the circuits? Loops or common mode current. We saw that also with the keyboard. How does a radio transmitter making signals at hundreds of megahertz make a DC signal in an electronic circuit? It's by rectification at PN junctions. And what is the basic structure that leads to these problems, PN junctions? What limits the effectiveness of a capacitor or an inductor? And mentioned parasitic inductance and capacitance. So a capacitor has parasitic inductance and an inductor has parasitic capacitance. And what are three ways to influence EMC of electronic circuits? We can reduce the loops, make them smaller, or we can shield, we can add filters, and we can watch out for PM junctions. I did have one more example of how we fix that circuit with the LED. If you put inductance on the transistor base through a bead or something, that will make it much better. And that's done a lot for discrete components. But there's nothing you can do here if it's in an IC unless you can
I'll call them.
put something on the input line. Maybe a bead on the input line might help. So that's I think the conclusion of our section now, right? So I'm going to stop sharing. You're on mute, I think. Okay, we're going to have a 5-minute break for the next speaker. So I'm going to stop sharing somehow.
Go over to me for a second.
Yeah, can I make you?
Yeah, make me the host for a second there.
Okay, if I can figure out on mine how to do this. Make host. There you go. You're host right now.
The house is a mess. The
Honey.
bathroom is disgusting.
Don't worry about it, please.
What time is?
I have no idea. I have a doctor's appointment in the middle of the day. He said he would call. I don't hear from him. I will call him.
Do
Okay.
you want this for anything?
Okay, great. Neil W2NGG, can you please mute? Thank you. So
Sorry, I was muted before. Someone unmuted me.
I see. Well, we all have our helpers, right? I mean, I understand that. So anyway, while we're getting ready to switch over here, I will read Mark Stefka's bio, then we'll flick it over to him. In fact, Mark, do you want me to give you control right now so you can get your video going?
Sure, let's give it a try. Can you hear me okay?
Yes, yes.
Okay, thank you.
So I'm gonna make you the, okay, so Mark will be our host here in a minute. Our next speaker is Professor Mark A. Stefka. Mark is a lecturer with the Electrical and Computer Engineering Department at the University of Michigan Dearborn and a professor at the University of Detroit Mercy. His university responsibilities include teaching undergraduate, graduate, and professional development courses on electrical and electronic circuit design, electromagnetic compatibility, antennas, and electronic communication systems. He was selected as an IEEE EMC Society Distinguished Lecturer and is the recipient of the IEEE Lawrence G. Cumming Award. And that award is the EMC Society's highest distinction. Mark Stefka has over 35 years of extensive full-time industry experience with military, HF, VHF, and UHF secure communications, spacecraft instrumentation, automotive electronics, and industrial electronics. Mark holds patents on methods for electromagnetic interference reduction, as well as aircraft and ground vehicle antenna systems. Professor Stefka is the author or co-author of textbooks and book chapters on EMC, as well as numerous technical papers presented at IEEE and SAE conferences and symposiums, both as a technical session participant or an invited speaker. Mark Stefka, over to you.
Thank you very much. Appreciate that. Scott, you mentioned that I have over 35 years of experience. I just want to point out to everyone online, especially some of the younger folks, that 36 years ago, my hair was thick and dark.
Excellent.
So, matter of fact, there's a picture around. You know what? Hold on.
How many times do I have to hear that joke?
One more time.
You will hear it till the day I pass to the other side of eternity, and then you'll hear it in your sleep. Here you go, everybody.
I gotta stop hanging out with you EMC people.
There you go. Here's 36 years ago. How about
That's
that?
your son? Who's this guy?
Yeah, exactly. All right. Enough about that.
I've seen that photo in the Hall of Shame down at U of M Dearborn.
You have, as a matter of fact. Yeah, well, that hallway.
I've actually seen that too.
Yeah, that hallway no longer exists, thankfully.
Oh, okay.
Yeah. So
I'm gonna request bring it back with a full blown up picture of you.
Yeah. Oh, I can see I must have some of the officers of my fan club online here this evening. This is great. Then
we call them.
Yeah. So, all right. Let me go ahead and thank you, everyone. I appreciate you taking time out of your life to be a part of this. And what I want to be able to do is kind of walk through some topics that I have discovered. A lot of engineers, a lot of students, a lot of engineers really haven't had an opportunity to really kind of look at some of the fundamentals of transmission lines and antennas. And what's interesting is maybe at one time, 36 years ago or 40 years ago, a transmission line was an intentional transmission line. An antenna was an intentional antenna. But now things have changed as we see our electronic systems, higher and higher clock speeds and so on. We start to produce things like unintentional transmission line effects, unintentional antennas. And Candace and John, you talked about the effect of antennas are great when you want them. They're bad when you don't want them. Transmission lines, again, have some characteristics that are great when you know about them, and it's bad when you don't understand what's going on. So that's what I talk about a little bit this evening. And just want to say that, even in these times, I hope everyone had as a good a holiday season as possible. And since I do since my life has transitioned from full-time industry to academia now, in academic fashion, I do have to start out with a quiz here. And the quiz is, many of you have heard of this gentleman called Albert Einstein. And Albert Einstein was known for a few things, but most specifically, he developed his theory of relativity, and it basically has to do with mass and time, energy, so on. Does anyone know exactly what portion of the year Albert Einstein came up with that? It was based on some observations. Anyone know what time of the year he came up with that theory?
I'm going to guess Christmas.
Yeah. It turns out it was actually during the holiday season, because what Albert Einstein discovered is that when you are with the mass of your relatives, your energy decreases and time moves slower. Scott, I should have had a recorded drum roll and cymbal crash on that one, I guess.
Agreed.
Yeah, exactly. So, like to go ahead and get started. I would love to be there in person with all of you, and since I can't, if you would, I really want this to be a dialogue. So if you have questions or comments as we're working through the material, or if you have jokes that are funnier than mine, I know that's kind of amazing to imagine that concept, but if you do, let us all know. I'd be happy to steal those and repeat those in my classes in the future. And I prepared some notes and some things I want to go over this evening. And it also turns out that I noticed I have some previous students with us this evening. Of course, I have a number of my colleagues I've known for a number of years. So I'm all prepared for those questions that I can't answer. I have a response for that. And here we go. And hopefully you can see what that response is then.
Mark, where's the human body model that I made?
It's residing in an honored place then.
I think you should have brought that.
Yeah, perhaps. Or it depends. Okay, let's kind of head into this then. What I want to talk about are some really key things when it comes to transmission lines and antennas. And specifically, I want to talk a little bit about theory of antennas, transmission lines. We're going to touch on a little bit on mathematics, and we'll look at some actual antennas and transmission lines. And what my goal is after this evening is to give you some insight as to when you're looking at antennas, again, intentional antennas, kind of understand what their characteristics are, or when you're looking at your products or your design, give you some tools to help you spot those unintentional antennas, which are so critical in EMC. And likewise, understand some characteristics of transmission lines. And I have discovered that this is something that a lot of folks just have not had an opportunity to really kind of study. So we're going to talk about that. So first thing I want to do here is ask two questions, and that is every current must return where? Every current must return to its source. Yeah, it'll get there somehow. It'll get there either the path that we wanted or the path that we had not expected. Every current will return to its source. And of course, the other key thing is that, whoops, sorry about that. The other key thing that we want to talk about is the fact is that the current, or the majority of the current, takes the path of least what?
Impedance.
Absolutely correct. Least impedance. There's some people out there that that make a statement that current takes the path of least resistance. That is not true. Now it may be at a frequency, the path of least resistance also happens to be the path of least impedance. However, current takes the path of least impedance. I'm going to abbreviate that by the letter Z. That actually with a line through it. I guess that's the way it's done in Canada. So let's kind of jump back and look at basic circuit theory. And what basic circuit theory tells us, or what we want to understand in basic circuit theory, is the following: is that if we have some kind of a source of energy, we have a source of energy, and let's say we have an impedance connected to that source, or perhaps that's even the source impedance itself, and we have a load, we're going to call this Z sub L. So again, I'm representing this is drawn as a resistance, but this is impedance. Now, I have a source impedance, I have a source voltage, a source impedance, and a load. And of course, we know that the maximum power transfer takes place when Z sub S is equal to Z sub L. And this is interesting because this is really the basis of a significant part of our circuits and our devices and our design. We want to have maximum power in the load sent or received from the source. Can anyone think of when we don't want this, when we want the source impedance to not be equal to the load intentionally?
The line. Power
When?
line. Power line.
Power lines, yeah, power lines. Where else? Filter.
Shooting.
Filter.
Sorry, what's that? There was a question or a statement. Filtering. What's interesting, in filtering, we actually want to maximize the mismatched. And John talked about doing filtering. But what's important is we want to maximize the mismatch at whatever frequency we are talking about. So again, this brings us back to the concept of impedance, not necessarily the resistance. Yeah, thank you for the comment about the other examples where we don't want to have a match. So let's take a look at what what I like to call kind of classical electromagnetics. And classical electromagnetics tell us some really important things then. And of course, the first thing is that classical electromagnetics tells us that whenever we have a changing electric field, I draw this electric field just a vector in this direction. So this is our electric field. I have it pointing up, vertical orientation. We know that whenever we have a changing electric field vector, we will have a changing magnetic field vector. I don't know how to draw in 3 dimensions just yet. However, imagine this kind of coming out from the board. And then we know if we have a changing electric field, a changing magnetic field, that those create what's known as electromagnetic wave, and that will propagate at some velocity, and we call that the speed of light. And the speed of light generally is about 2.99 something times 10 to the 8th meters per second. There's 2 ways to do things. There's the hard way, and then there's the what?
Engineering way.
You got it. The hard way and the engineering way. So we're going to do this the engineering way. And 2.99 times 10 to the 8th meters per second is somewhere around 3 times 10 to the 8th meters. Oops, 3 times 10 to the 8th meters per second. Close enough for what we're trying to do here. All right, let's look a little bit more in detail now at the electric field vector. And we measured the electric field vector in an interesting way. I guess the best way to explain this is, where would you find an electric field, or where would you find an intentional electric field? Oh, no.
Power lines.
Well, okay, yep, power lines. And let's kind of scope that down a little bit. This thing called a capacitor. And a capacitor, the purpose of a capacitor is to do one thing. It's to store energy in the form of an electric field. And a capacitor has an electric field that is created between those two conductors. So we have a conductor and another conductor separated by a dielectric. So we have an electric field. This is an electric field because it has magnitude and it has direction. The magnitude is proportional to the amount of charge that's contained in that capacitor. And then we measure, or we quantify that electric field in the following way. We might talk about the distance between these two conductors, and I'm just going to say this is 0.1 meter. However, 0.1 meter, however long it is, I don't know, because I was born in the United States, but I guess it's whatever. It's probably a small value here. Actually, it's about 4 inches. And let's say that we have a magnitude of 10 volts applied across that capacitor, and we have a distance between these two plates of 0.1 meter now. This would now mean that we have an electric field which has a direction, which is perpendicular to the plates, and it has a magnitude, and that magnitude is now 10 volts divided by 0.1 meters, or in other words, what's the electric field strength then?
100 volts per meter.
Yes, sir. 100 volts per meter. Does that make sense? I don't know, I guess. Okay. Where do we want that electric field? We want that electric field to be where? Stay inside the capacitor. If we lose the electric field, how good is the capacitor for us? It's no good. And John talked about that. Sometimes our devices don't act the way we thought. All right. Now we talked about electric field. Let's kind of flip this, or let's kind of focus on or look at the other component, which is the magnetic field. And the magnetic field we can look at in the following way. How do we create a magnetic field? Well, if you go back to think about physics, and what physics tells us is, if we have a conductor and we send current down that conductor, let's just make this current I. Remember the old right-hand rule? Right-hand rule says, put our thumb in the direction of the magnetic, thumb in the direction of the current, and our fingers will wrap around the conductor. That shows us the direction of the magnetic field. Interesting. Maxwell's equations tell us something about the magnetic field. The magnetic field always has to form a complete loop, or basically closes back in on itself. So that is why I do magnetic field shielding. Basically, the best we can do is contain the magnetic field in a controlled way. All right, how do we express the magnitude of the magnetic field? I'm going to just call that H for the purposes of consistency with a lot of other EMC folks. It turns out that we say a magnetic field has a magnitude, a direction. The direction is wrapping around that conductor. How do we create a magnetic field? We create it with current, and we would call that amps, or amps of current. And in this case, though, we might measure the magnetic field at some distance R. And it turns out that the magnetic field is measured in the following way. It is, let's just say this is, let's make this 10 amps. So we have 10 amps divided by whatever this happens to be. And I don't know, let's make this 0.5 meters. turns out we are talking about the perimeter at a certain distance, or the perimeter of this circle. So this would be 2 pi r, and of course if r is 0.5 meters, what am I doing here? What is the magnitude of the magnetic field vector? This is 2 pi times, okay, all right, that's 10 divided by about 3. Again, there's 2 ways to do things, the hard way and the engineering way. It's about 3. So this means we have a magnetic field of about 3 amps per meter. Okay, questions on that? All right, the other thing that, and talking about a changing electric field and changing magnetic field, we would say that it obviously if it's changing, we would say it has some frequency or some period associated with it. So let's look at that for a second here. And so this is our frequency of our electric field or magnetic field or electromagnetic wave. And of course, we know that we have some, let's say, period t across here, and f is equal to 1 over t. So this becomes the frequency then. And then in the case of a radiating electromagnetic wave, then we would say, let's see, f is equal to 1 over t. So this is, well, whatever, this is a frequency. Then we can talk about something else. We can talk about how fast the electromagnetic wave propagates and how far it goes from the source as a function of frequency. And that is known as wavelength. And wavelength is v sub 0, speed of propagation, divided by frequency. Okay, so what this says is something interesting. As the frequency, what do we know about v sub o, speed of propagation? Do we know anything about that?
Yeah, 300 times 10 to the 6 meters per second.
Absolutely. Does that ever change?
Yeah, it depends on the materials.
Yep.
Yeah, it depends on the material, but yep, absolutely.
In free space, it does not.
Yep, absolutely true. So in free space, let's just talk about free space for a minute. And thank you for the comment about the other material. Free space, it's 300 or 3 times 10 to the 8th meters per second. I'm going to change that. I'm going to make this 300 times 10 to the 6th meter per second. I didn't change anything. Let's pick a frequency. I don't know. Somebody pick a frequency of an electromagnetic wave.
100 megahertz.
100 megahertz. Thank you. Whoever said that, you are my hero of the evening. 100 megahertz. And why do I like 100 megahertz? Because I can do a bunch of different things with this. Quick comment. If this is megahertz, we know that this is 100 times 10 to the 6th hertz. We get rid of that. We can get rid of that. This now becomes 300 divided by 100. This hertz is cycles per second. The seconds cancels out, and that means we got doot, 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 doot. So for 100 megahertz, we have a lambda of about 3 meters. Okay, so what's that mean? That means in one cycle, the electromagnetic wave has propagated how far? 3 meters. Okay, as frequency goes down, what happens to the wavelength? As frequency goes down, the wavelength
Goes up.
Goes up. So the frequency goes down. There's longer time then. Longer time means that that wave is going to propagate a longer distance, further distance. So the wavelength increases. Okay. All right. So let's move on from there. Let's talk about transmission lines. And turns out there are a couple different types of transmission lines. Then, and transmission lines are generally designed, hopefully designed for their particular application. I guess transmission lines are sort of like plastic. Then, does anyone I assume everyone has seen plastic before. Does anyone know how many types of plastic there is? Anyone have an idea?
Endless,
What was that?
endless different types. There's some with shielding. There's hard
No.
plastics, soft plastics.
Yeah, it would seem like there's all kinds of different kinds. It would seem like there's all kinds of plastics, doesn't it? Did you know it turns out there's only two kinds of plastic? Plastic that's broken and plastic that's going to be broken. Scott, no drum roll for that again either, right?
Bing.
Yeah, there we go.
No, just students crying.
Yeah, okay. That only happens during final exam season. All right, let's look at transmission lines. So when we're talking about transmission lines, typically we're talking about a specific type of transmission lines, and one type of transmission line, which I'm sure a lot of you are familiar with, are something called the coaxial cable or coaxial transmission line, and the other one is TWP, which stands for twisted wire pair or wire pair transmission lines. And it turns out that coaxial is actually, it's E field. It provides electric field shielding. And remember the way the world works: happy, sad, good, bad, day, night, electric, magnetic. Absolutely. This provides H field shielding. Okay. And I guess kind of, sort of, perhaps we can talk about another type of transmission line. And it turns out that we can actually have transmission line made up of traces on a printed circuit board. This sounds like a crazy concept, because normally when you think of a transmission line, you think of what? You think of this kind of stuff, right? You think of these in this case, this is coaxial cable with what? These giant, connectors on the end. Or you might think again of twisted wire. Maybe you can kind of see that. If we were there, I would pass this around and hope that I would get it back later, but maybe you can see we have two conductors there. All right. So transmission lines. So we have the intentional ones, coaxial cable, twisted wire pair, and then we have traces on a printed circuit board, which sometimes turn out to be unintentional transmission lines. Okay. All right. Well, when do we create or when we talk about transmission lines, what do we mean by that? This is essentially the definition of a transmission line is a following. It's interesting because a transmission line is really defined as a function of the wavelength of the signal that it's conducting and its physical length. So let's take a look at a schematic. Assume we have a schematic and we have device A and we have device B on our schematic. And this maybe is a source, maybe this is a load. And our schematic says we have a conductor going from this point to this point and a conductor going from this point to this point. What does that schematic tell you about the real world?
Not a whole hell of a lot.
Exactly. I was going to say, I know Joanna knows the answer to this one. That doesn't tell you a lot at all. All it says is this is what the designer hopefully, or this is what the designer hopes is taking place, that they have energy, or as was discussed earlier, differential mode current flowing in this direction, source, and a return. That's what the designer hoped for. Well, it turns out as the physical length between these two devices becomes longer and longer, we get something interesting going on. Let's look at this. Conductor and a conductor. So we have a conductor and a conductor, and let's just say it's on a printed circuit board for a minute. Conductor, printed circuit board material, and a conductor. Printed circuit board material is a dielectric. It's an insulator. Should be, because we want our circuits to work. Conductor, insulator, conductor. What's another name for that?
Capacitor.
Capacitor. Absolutely. There we go. Where would you find the capacitor on the schematic? Probably you wouldn't. Is it there? Yes, it's there. John talked about that a little bit ago. What else do we have going on? Well, we also have, when we have current flowing, differential mode current, or we have current flowing, we know we have current flowing, let's say from here back to here, current is now flowing in, we would say current is flowing in a loop. Whenever we have current flowing in a loop, or whenever we have current flowing, we have a magnetic field. Whenever we have a magnetic field, we're going to call that phi, and that is created by some I that is defined as L, which is inductance. So it turns out that we actually have inductance now. Interesting. So we have two conductors, and the intention was to send a signal or power or whatever from point A to point B. We now have conductor separated by dielectric. It also forms a loop. We have something called a lumped equivalent circuit model. Okay, a lumped model basically talks about this overall capacitance between here and here, and the overall inductance in this loop. Well, once we effectively, this is when L is less than about 10% of lambda. There's lambda. We just talked about that a little bit ago. When the physical length L from, and by the way, yeah, this L, these two L's are not the same. The L with it. All right. So this L, it means the physical length. When the physical length L is less than 10% of a wavelength, we would say that we have this lumped model. Now, something interesting takes place. Keep everything else the same. Everything else the same. This is the same circuit. This is the same circuit. All we're doing, we're going to move those apart or spread those apart. And I'm just kind of reading a chat here. Okay. Something, Michael and Melissa.
You need to download the HBM.
Download the what?
HBM. The picture
The ACM.
It's the human body model that I said.
Oh. All right. I respectfully request that Melissa be muted for the rest of the evening. So let's take this. Let's spread these apart now. I'm going to take A and I'm going to take B, and on the schematic, these still look the same. So this is A and this is B, but now it turns out that my physical length L here is greater than 10% of a wavelength. And what happens is when we say, or when this is physically greater than 10% of a wavelength, we effectively get current and voltages that are out of phase. And this capacitance and inductance now is not represented by a lumped model. It's best represented by a distributed model. So we will take this capacitance and we will basically distribute it now across this entire transmission line. And we'll take the inductance and we'll distribute that. Okay. What's the value of the sum of these capacitors? It's going to be equivalent to this lumped. What's the value of the sum of these inductors? It's going to be equivalent to this lumped model. Again, L is now greater than about 10% of a wavelength. Okay. Is that a good thing or is that a bad thing?
It depends.
On what? What's it depend on?
Or whether you take that into account or not.
Absolutely. Absolutely. So let's say we send some energy from, we want energy from point A or from device A to device B. We throw the switch here. We throw the switch and we send a pulse of current or a voltage pulse out there. When does that pulse get down here to point B?
Whatever the speed of propagation divided by the length.
Absolutely. Is
Or
instantaneous.
times the length, sorry.
Yep, that's fine. I know what you meant. Absolutely. Is it instantaneous? No, it can't be, because again, that goes back to violating whatever Einstein said there. Okay. It turns out this effect becomes even more pronounced in the case of a transmission line, and this is fundamental to a transmission line. Essentially, the energy starts out here at device A, and it flows in this loop, and then what happens? It charges this capacitor. And then it what? Flows in that loop. Charges that capacitor, it flows in that loop. Charges that capacitor, flows in that loop, and effectively ends up here, out here at the load. If you're looking at transmission lines, you'll typically see something called the VF. And the VF, in the case of a transmission line, is known as the velocity factor. And what it means is what portion of the speed of light is this energy propagating. Most transmission lines, 60, 70, 80% velocity factor. Okay, does that make sense? I don't know. When you want to know if something makes sense, what do? You go where?
Google.
Yeah, you go to the internet, and I'm going to attempt to pull up a link here, I hope. So let's see. How do I do that? Let's see, share. How do I pull up a link? Someone give me
share your screen, but I'm muted, so you can't hear me.
Okay, share screen. I want, no, that's not.
Desktop or your internet browser.
Okay.
I think probably his browser, since it's a URL.
Well, here, let me do this. I'm going to hit a button here. Okay, and I'm going to see. Let's see here. Let me get the browser going.
Looks like you could use some help.
And naturally, you get a commercial. Okay, let's see. So I want to.
If there's audio on your link, make sure to check the box that says share computer audio.
Okay, all right. For this, it's not critical that you hear the audio, but that's okay. Help me out here. Oh, wait. Mute, stop, rename, spotlight, hide self-use, spotlight. Share screen is what I want?
Yeah, yes.
Yes.
Share screen.
The green icon.
Ah, there we go.
With the little arrow and the screen.
Yeah, there we go. How's that?
Now we can see your screen.
Perfect.
And some dude, he's holding the window, I think.
Next to the window.
Start at swisscode.com for all your replacement hardware projects.
To send an
Okay, what do you see?
The transmission.
Need to send and we hear it too. So.
Thank you.
electrical signal, we need two wires. Since two metal conductors are by definition a capacitor, this means that each section of our transmission line has some capacitance. And since a loop of wire is by definition an inductor, each section of our line also has some inductance. Suppose we close a switch, applying a constant DC voltage across our two wires. This capacitance and inductance is what prevents the signal from traveling instantaneously. Therefore, we can never eliminate this capacitance and inductance completely, because this would then violate Einstein's theory of relativity, which states that information can never travel faster than the speed of light. These capacitors and inductors shown are not components that we deliberately add to a circuit, but are an inherent part of all wires that carry electrical signals.
Okay, so if it's on the internet, it must be true. And I'm going to attempt to get back to my, let's see, stop share. There we go. Okay, questions? Can you see me okay?
Yep.
Okay, questions on that? All right.
What about the return line? Shouldn't there be inductance in the return line on the bottom?
Well, wait a second here. Yeah, here we go. There we go.
Oh,
yeah. No, that's a good question. You know, from a theoretical standpoint, does it matter? I don't know. All I know is we have some distributed inductance. What I generally do, just for a symmetry standpoint or symmetrical standpoint, I essentially allocate the loop inductance into segments of partial inductance. And I just allocate that across the both the source and the return line. Does it matter? I don't know. Maybe someone else can comment on that. Okay.
It made a nice demonstration to see the return reflection also in there. And you wouldn't have been able to see that if the other line was moving. You would be distracted.
Yes. Yep. And you know what? I will send Scott the link for that video. You can sit and watch that over and over. You know, normally during the holiday season, I put that on my big screen TV, and my my family come over and they said, when do we watch the transmission line video? I said, no.
Did you give out Christmas cards of your human body model?
So anyways,
you need to give out Christmas cards of that human body model I made.
Mute. I'm requesting Melissa be muted there. All right. But the important thing is what? The important thing is we recognize how that energy propagates along the transmission line. A key parameter in the case of a transmission line is known as the characteristic impedance. And let me show you let me write that equation down. There's all kinds of mathematics behind this for the purpose of what we want to accomplish now. Again, the key parameter is the characteristic impedance, and the characteristic impedance is defined as the following. Z is equal to the square root of L over C. And actually, there's some real terms out here, some resistance and conductance. You know what? That stuff really doesn't matter. The impedance of the transmission line is governed by the square root of L over C. What L and what C are we talking about? Are we talking about the lumped L, or are we talking about the distributed L?
Distributed L. It's Henry's per meter divided by Farads per meter.
Yeah. You know what? You're right. Although if you think about it, it doesn't matter, because if you normalize, get rid of that per meter or per inch, it doesn't matter. So you can be talking, you have a piece of transmission line, if it's X number of Henrys in loop inductance and X capacitance for a fixed length, it doesn't matter. Normally,
you are correct.
Yeah, normally we would say for some length, but it doesn't matter because we've taken that lumped element and we have now distributed that. Okay, so important concept is the characteristic impedance is equal to square root of L over C. How do we change the characteristic impedance? Easy. We change the characteristic impedance by either changing the C, meaning we change the distance between the conductors, or we change the L, which is changing the loop. If we move the conductors farther apart in a transmission line, farther apart, what happens to the characteristic impedance? Go up or go down?
Increases.
Yeah, because we have a capacitor or capacitance. If we increase the distance between those, that means the capacitance goes down. When the capacitance goes down, the impedance then goes up, okay? Which is why you'll see different transmission lines have different characteristic impedance. RG58, which is 50 ohm, RG59, which is 75 ohm. We have something called parallel wire, which is 300 ohm, and so on. The important parameter is understand that the impedance is a function of the inductance and the capacitance. Okay, questions on that? All right, let's talk about a printed circuit board. Can we have transmission lines on printed circuit boards? Well, a printed circuit board, it depends. Absolutely. We have a printed circuit board, and let's say we have a clock circuit here, and let's assume we have a microprocessor over here. What do we know? We probably want to send a clock signal down along here and the return clock signal along here. Look at what we have. Source, return, conductor separated by a dielectric. So it turns out, depending on the clock frequency then, which determines the wavelength, and depending upon the length, we can actually have transmission lines on our printed circuit board. Who cares? Who cares? Well, I think, Kimball, I think that was you talked about the reflections.
Not sure.
Oh, okay. Well, as, someone made a comment about the reflection. Who cares? This goes back to basic circuit theory. If it turns out we have a transmission line on a printed circuit board, either intentional or unintentional, we probably want to make sure we get the correct impedance. So we want to match the impedance of our output circuitry to the impedance of our transmission line to the impedance of our load. So all this stuff really, really, really kind of plays together. Questions on that? All right. Ready to move on to antennas now. So here is the question. If we have a source of energy, so this is a source here, and we have a light bulb here. Many of you have been through circuit theory classes before. We would generally connect the light bulb, let's say, to here, and connect the light bulb to here. If this is a source, and we have connected the light bulb in the following way, what would you expect to have? What would you expect to happen?
For me, it would burn out the light bulb.
Yeah, but the light bulb will probably glow for a while, hopefully before it burns out, right? Okay, so here's the question. If I were to disconnect this path right here, what would happen to the light from the light bulb?
Oh my God, it went off.
It went off. That's right. Okay. What if I were to disconnect this? What would happen to the light bulb? Would it go back on?
Unfortunately, no.
Right. Exactly. Unfortunately. So what do I got? I got a connection hanging out in space. I got a connection hanging out in space. All right. Will that light bulb light? How many people say yes? No?
It depends.
It depends. Yeah. How many people don't really care at this point? Well, it turns out it actually depends. What's it depend on? Well, again, let's take a look. I found another wonderful video, so let's see if I can get that going here. Let's see. I need to turn that one off. And okay, hit that, and let's see. Oh, wait. All right, wait a minute here. So I need to share screen. Is that how I did that?
Yeah, the green up arrow.
Yes, it's how you did that. You shared the browser and you made sure you shared the sound.
Mute. Okay, so what do you see on the screen right now? Hopefully it says
Dipole antenna, MIT, physics lecture. Yeah, you got the right one.
So here we go. If it's from MIT, you know it has to be what? Right. So we have a power source. We have something called an RF transmitter, whatever that is. Something called a transmitting antenna, whatever that is. And something called a receiving antenna. Again, whatever that is. If you'll take a look, right at the, I love these vacuum tubes. Take a look at the center of the receiving antenna. We have a light bulb. And the light bulb is just connected to whatever these things are hanging out in space. Is this light bulb connected to the power source?
No. Not with physical connections.
Is it connected to the power source?
It's in the same world.
Here we go. Ready? The light bulb is not lighting. I would probably say it's not connected. Here we go. The light bulb is being lit. Is the light bulb connected to the power source?
Yes, it's being lit.
It's now coupled to the power source.
Where's it getting its energy from? From the power source.
Yes.
Yeah. So we would say it's connected to the power source, right? Has to be. When does the light bulb become the brightest?
When the antennas are parallel.
Yeah, or in other words, the capacitor or the capacitive coupling is a maximum. Is there a circuit there?
Yes.
Absolutely. Can you see the circuit? Absolutely not. I love this video. Questions on it? Okay. Again, I will provide the links to Scott on that. So how do we change this? We can change this really simply. Conductor, 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 conductor. We now have what? An electric field, and sets up a current flow through there. So what's the purpose of an antenna? There's only one purpose of an antenna, or an intentional antenna. That is to what? Send energy how? Without wires, without a conductive path. A conductive path. And say we do it via a radiated path. Okay? Well, like in anything else, again, there's happy, sad, good, bad, day, night, electric field, magnetic field. It turns out that there are two kinds of antennas in the world. And what are those antennas? There are antennas that work on the, quote, electric field. And how do we make an electric field antenna? It is really simple. We take a conductor and we take a conductor and just separate that by dielectric. And what do we connect? We connect it to a transmission line. Okay. What does this look like? This looks like a capacitor. How good of an antenna is a capacitor? Well, it's not. It's intended to hold an electric field. So how do we make a capacitor turn into an antenna? We do this like this. We have, hopefully you can see there, we have conductor, conductor. How do we turn this capacitor into an antenna?
Turn them 90 degrees from.
Yep. Open it up. This is a pole. This is a pole. This is known as a what?
Dipole.
Dipole antenna. A dipole antenna is really nothing more than an open capacitor, and it's an electric field antenna because it has capacitive coupling. Question on that? Okay. I know someone's ready to ask the next question. Next question is, what about a what?
Magnetic field antenna.
Yeah, absolutely. How do you create a magnetic field? Current and inductance. This is a magnetic field. It looks like a what?
A loop.
A loop. Or in some ways you might almost say it maybe is a second, it's a winding of a transformer. Oh, I sure wish I was there with all you folks. Okay, so whenever you see a loop, that generally means magnetic field. I think John talked about that. Whenever you see a dipole like this, that means electric field. Okay. Key parameter in the case of a dipole antenna, and that key parameter is the following. And so let's look at let's draw a dipole antenna. And it turns out that we know that we have capacitance between the two poles of that antenna. And we also have inductance. As you may recognize this as series inductance and capacitance. And we want X sub L to be equal to X sub C. And when X sub L is equal to X sub C, what do we call that?
Resonance.
Resonance. So it turns out a dipole antenna has this property called resonance. And resonance actually occurs at lambda, resonance actually occurs at L, the physical length of the dipole antenna. L is equal to lambda over 2. So what's that say? That says all things being equal, as we change the length of our antenna, either intentional or unintentional, the resonant frequency will change. Is that a good thing or is that a bad thing?
Depends.
Absolutely. If you want to use an antenna for some specific purpose, you probably want a resonant antenna. If you for some reason create a resonant antenna structure in your product or your system, your device, it may be a really, really good antenna and cause you now to fail. Radiated emissions and all other kind of bad things could happen. Questions on that? A dipole antenna has an interesting parameter, and this is not 100% correct with our physicists. If we have physicists online, I'm glad I'm not there in person because you'd be throwing things at me right now, but that's okay. There's something called radiation resistance, and radiation resistance means how good the antenna is in sending out energy, and radiation resistance for a dipole antenna is somewhere around 73 ohms. And it says it looks like a 73 ohm resistor. Okay. There are times when dipole antennas are kind of unhandy. And, something like this, if again, John talked about, walkie-talkies, a dipole antenna on this might, end up poking out people's eyes then. So we do something interesting. We take the dipole antenna and like this, and what do? We just basically cut off one half of it, or we make the return path, maybe, the structure of a car or a vehicle, or someone's holding that. It means we end up with one half of a dipole antenna. Would you expect a half of a dipole antenna, or what would you expect the name of half of a dipole antenna to be? It's a what?
Monopole.
Monopole. Is a monopole perform better or worse than a dipole?
Depends.
Well, actually,
has higher gain.
Yeah, actually, Michael, it really doesn't kind of depend. A monopole antenna is going to be worse than a dipole. It effectively has less ability to transfer energy. So it turns out the radiation resistance or how efficient a monopole is, the radiation resistance is about 37 ohms. Okay. If we were to make that monopole even shorter, would it be a better antenna or a worse antenna?
Worse.
Worse.
Yeah. How bad is too bad? Well, exactly. There's an old phrase in ham radio land, a bad antenna is better than
no antenna.
Exactly. There you go. So generally, as we reduce the size of the antenna, the radiation resistance goes down or the efficiency goes down. So there you go. Questions? Comments?
You're just about out of time. Is that the end of it, Mark?
Yes. This is what I plan to cover for this evening. I looked at the schedule. I see Karen is scheduled at 7:30 Eastern time. So we got a minute or two. If there's any questions or comments from anyone, be happy to do that. Okay. Oh, go ahead. Sure.
It's not a question or comment. I'm just saying I now have the human body model as my picture. So now you can see it.
Yeah. Okay. All right. So based on that comment, I want to point out one other thing here. And in Candace's slides, and you can tell we perfectly coordinated this. Candace had some interesting antennas on her slide. And one of those kind of looked like this, which looked like a single pole then. And one of them, remember, looked like a loop. And one of them looked like two ice cream cones stuck together. Okay. And one of them kind of looked like some fish bones and that. All right, so here we go. Based on what we just talked about, a single pole, is it an electric field or magnetic field?
Electric.
Absolutely, electric field. A loop, electric field or magnetic field?
Magnetic.
Magnetic. Two ice cream cones stuck together, electric or magnetic?
Yes.
Turns out it's actually electric field. And what's interesting is the way these are supposed to work, this actually looks like two cones. So it's called a bicone, or in other words, a biconical antenna. And what's interesting about a biconical antenna, it effectively looks like a number of different length dipoles in parallel, which of course would be effectively kind of resonant at a very, very wide frequency. We use those all the time in EMC.
Yes, we do.
Yeah. So, all right. So there you go. It's 7:30. Thank you, everyone. Scott.
Thank you, Mark, very much. If you could please turn over control to Karen for us.
Sure. How do I do that?
Well, you find Karen in your little, can you see a bunch of people on your screen? You see Karen near in the top row next to me, maybe?
She's, let's see, she, okay.
If I talk, it might bump me up.
Look in the upper right-hand corner and you'll see 3 dots on Karen.
Oh, make host or make co-host?
Yeah, make co-host actually. Well, whatever, host is fine. Host is
all right. Karen is the host now.
Okay, let's see what happens. I still see you. You got to say okay. I think you got to click okay.
I did say okay.
Karen, you got to share your screen and that will flip.
Scott, to me it says that I'm host now.
Okay, I think we might have you now.
So I think I'm good.
Is your share screen button working?
It is green. Let's see if it actually works. I'm going to share my entire screen. Oh,
they're all green, so that doesn't mean anything. You have to just try.
Nope, still grayed out.
Okay, Mark, give it another try.
There's 3 or 4 dots in the upper right
of Karen's screen, of Karen's image. Click that and say make
chat.
host.
All it says is chat or pin video.
Should be one that says make host, right?
Well, it did at one time.
Well, maybe Karen, you double check you.
No, Karen is the host now.
Okay. Karen, you are the host.
So why isn't it letting me share then? So choose what you'd like to share.
I can't.
Huh. Oh, there's why. Okay.
Found it?
Okay. I think I got it.
All right.
I see Scott.
Hey, that's me.
Yep.
Now you should start.
Now we see useful equipment.
All right, let me introduce Karen real quick, then get her going. So
did we want to take a chance for a break first, or plow right through?
Does anybody want to take a break? We need a break.
Plow right through.
Okay, I guess we're going to plow through. So our next speaker is Karen Burnham. Karen is a principal scientist at Electromagnetic Applications in Denver, Colorado. She is an EMC engineer with experience in both the aerospace and defense and automotive industries. At NASA JSC, she worked on the Orion spacecraft and pyrotechnic systems. She was able to work on the Dream Chaser spacecraft and F-35 fighter jet. She spent several years working at Ford Motor Company on traditional vehicles like the Ford Edge and Lincoln Continental, and also on the newest line of electric hybrid vehicles such as the Ford Explorer and Lincoln Aviator. She sits on several international standards committees and was recently elected to the IEEE EMC Society Board of Directors. Karen.
Great, thanks. And I just want to say, I moved to EMA and I moved to Denver, but I honestly miss Michigan and I miss everybody there, and I really wish we could be there in person. On the other hand, as Mark was talking, the sun was setting over the Rocky Mountains behind me at my office window, so there's some compensations there. But Mark is a very hard act to follow, so I hope that you will all bear with me. Okay, so I want to talk today about low cost SDR, so that's software defined radio for EMC purposes. And I want to caveat that right off the bat by saying that if, for instance, my good friend Kimball Williams or Mac Lunn were giving this talk, I suspect that they would have a very different emphasis, because I'm going to talk about how we can use SDR to visualize the RF environment around us and get information about what's out there that we don't necessarily know about. But if I were giving this talk from a ham radio perspective, and of course the ham radio community in Southeast Michigan is phenomenal, there's so much more that you can do with SDR if that's your goal. So I'll touch on that a little bit, but overall my focus is really going to be on how you can use it for potentially EMC troubleshooting. And a couple things that amuse me, it's going to end up being that every talk tonight is going to mention walkie-talkies. It's like we planned it in advance. So when it comes to useful equipment that you might use for EMC purposes, there's the list is endless, right? If we all had infinite money to spend, we'd all end up with garages upon garages upon garages worth of just useful stuff. So you can get yourself a handy multimeter that should never probably be too far from your side. If you want to make really high precision resistance measurements, like down into the milliohms, you might want to get a 4-wire milliohm meter. If you want to get really fancy, this was my favorite piece of troubleshooting hard equipment when I was working on the electric vehicles, which is a handheld spectrum analyzer. But that will definitely set you back a pretty penny. You can get a nice big network analyzer, or as Candace was mentioning that she got for Christmas, a nano VNA, which you can plug into a computer. I'd love to play with one of those. A set of near field probes that can come in handy, especially if you're looking at problems at the printed circuit board level. Everybody's favorite clamp-on current probes. These are good for finding out what's going on in your harnesses, especially those common mode currents that Candace and John were talking about that can cause no end of problems. And actually, I love this picture from one of the cover of one of Ken Wyatt's books. Ken is a consultant himself, and he's got this whole toolkit that he just can carry around with him. It's got all kinds of equipment that he's found useful over the years. Everything from blade antennas, near field probes, different kind of meters, different kind of clamps. This one is one of my favorites in the lower right. You see this little thing with a red button? That's a piezoelectric sparker that he probably pulled out of something like a barbecue ignition system. And the great thing about that is that every time you push that little red button, you're going to get this nice burst of broadband noise. And that can, potentially give you an idea of, for instance, if you have equipment that might be susceptible to that kind of thing, or you want to know how your system is picking up on noise across a broad spectrum, it's a cheap and easy thing to just carry around with you. But what I'm here to talk about today is low-cost SDRs, because even with the nice cheap equipment like a little piezoelectric starter, most of the time when people think of EMC equipment, they're thinking about stuff that costs thousands of dollars, tens of thousands of dollars. And of course, the folks who sponsor so many EMC events, right? Rohde and Schwartz, Tektronix, Agilent, or Keysight, they've got these amazing boxes that can do they pretty much can do everything but cook your dinner for you. They're so shiny and so amazing. It's so many functions and features and capability. But sometimes you don't need all that. Sometimes you just need something to, just in a very relative way, tell you what's going on in the local RF environment. And if that's what you're after, then boxes like these, just little things, the one that I'm going to use for my demonstration tonight is a NESDR Smart that I got from Newelec. And I should say I'm not affiliated with Newelec in any way. This is not meant to be an ad for them. It's really just, that's the one that was most appealing to me on Amazon because it came with some antennas and a nice antenna mount. But the actual NESDR Smart dongle is the part that actually plugs into the USB port of my computer. That is 2 inches by half an inch by half an inch. Tiny little thing, and the whole thing plus some extra antennas costs $30. So in terms of just investing in something that you can play around with, that has a lot of capability, you know, you could do a lot worse than starting this kind of software-defined radio system. And so the next thing I want to do is sort of to follow on from what Mark was talking about, because so we've learned now about antennas and how antennas operate. But what happens from the time the electromagnetic wave gets picked up by the antenna to the time when you either hear, you know, your AM radio, your FM radio, or you see a signal displayed on your screen, whatever screen that might be. And as such, there's a particular architecture that's become pretty much ubiquitous, and it's a super heterodyne receiver. This one is for AM. I'll show what how an FM one is different in the next slide, but this has got all the basic parts to it. So starting from the left, basically the aerial is your antenna. That's what's actually picking up the signal. And then you want to have a pre-selection filter so that we can imagine that an antenna picks up one and only one frequency, but that's obviously not true. Antennas are going to be more or less sensitive to a number of frequencies depending on their length. And so you want to narrow it down right off the bat that, for instance, if I'm looking for AM radio, I only want to pick up between 530 kilohertz and 1.3 megahertz, at least as much as possible, as much as reasonable. Then you might have an RF amplifier, so you're going to take those signals that you pulled from the antenna. You're going to boost them up to a level that's usable by the rest of the architecture. And then this is really the key to the super heterodyne receiver. And I'll go into a little bit more detail about exactly what's happening in the mixer in a couple slides. But you've got this thing called a local oscillator, and it's setting out a particular producing a particular frequency. And when you tune a radio, when you literally turn the knob to change the dial, or punch in the new frequency on a digital receiver, what's changing is nothing about the antenna, nothing about this filter, nothing about this amplifier. What's changing is the frequency put out by the local oscillator. Based on that change, this mixer is going to mix with ideally just the frequency of interest from your RF filter, and this is going to produce an intermediate frequency. That's what IF stands for. And so the intermediate frequency is always the same. So this filter is meant to pass only that intermediate frequency and nothing else. Again, that's the ideal world. It's never actually quite that simple. And then you're going to amplify that intermediate frequency and send it on to the transducer that actually puts out your audio output. And so that's the path from beginning to end, is that you pick out the signal that you want, but it's still a range of signals. You mix it with the frequency that you've selected from your local oscillator to produce an intermediate frequency that's then amplified and sent to your output. Again, whether that's a screen or what you're listening to, or however you're receiving your signal. For an FM receiver, the only thing that changes is that because, and again, as Candace mentioned, there are a bunch of different ways to modulate a signal to transmit information. Amplitude is amplitude modulation, AM. It's literally just how big is the signal that you're getting. FM, frequency modulation, so the information is contained essentially in small shifts in the frequency of the carrier signal. And since that's the way the information is transmitted, after you do the same architecture with selecting your frequency with your local oscillator, mixing it, producing your intermediate frequency, then you need a phase detector or voltage controlled oscillator to get the audio output that you want. And just for a little more detail about what's happening inside that mixer, so this one's for an amplitude modulated, but it can be anything. The frequency that's picked up by the antenna, we'll call that frequency 1. And then the frequency being produced by your local oscillator, we're going to call that frequency 2. As they combine in the mixer, when you combine different frequencies of waves, sine waves, cosines, mathematically as well as actually in the hardware, you produce this this product called the beat frequency, and that's what you can see here. And that's the absolute value of F2 minus F1. And so when you tune your radio, what's going on is that you're changing F2 so that it combines with the frequency you want from F1 to produce the same beat frequency, which becomes your intermediate frequency, which is then the thing that is actually transmitted to the user. Now you can see that that none of this is perfect, right? So antennas pick up more than just the one frequency that you want, even more than just the one bandwidth that you want. The mixer, of course, is an absolute value, so it's going to be producing frequencies not just F2 minus F1, but also F1 minus F2. So that can have the potential to cause some problems. And I hope that my colleague at EMA, his name is Matt Miller, I hope he won't mind that I completely stole this slide from him. But what it shows is that in these kind of radio systems, you can actually get unpredictable interference because of those multiple frequencies that are bouncing around when you didn't necessarily plan for them. And so, for instance, if you're trying to figure out if a particular transmitter will interfere with a particular receiver, you have to consider that the transmitter is not just putting out one frequency. It's putting out one frequency and a bunch of harmonics and some spurious emissions, and it's going through its heterodyne transmitter and then being picked up by the receiver, which again has the, because of the mixer products and because of additional susceptibilities, additional frequencies the receiver's picking up, all of these different elements that feed into it, a receiver can be susceptible not just to the frequency it's designed to pick up, but also to a number of others. And if you ever get a chance on LinkedIn, Matt Miller's got a really nice, like 5 to 7 minute video with 2 handheld radios showing how, that kind of very unpredictable out of band interference can happen. And of course, there's all kinds of ways to try and predict that, model it, and prevent it in advance. But this is just mostly to show that it's more complicated than it looks, right, from an ideal model. Now, okay, so it used to be that radios were these huge things that they'd mount in the back of trucks, right? If you've ever seen like World War II movies, you're like driving around in the communications Jeep, with the big electronics in the back. Obviously, we've come a long way since then. So everything's miniaturized, everything's going more and more digital. Software-defined radio as such is not a particularly new idea. It certainly was being proposed in the, I believe, late 50s, early 60s through the 70s. But as electronics become more and more sophisticated, and Moore's law with the how many transistors can you put on a chip has just shot through the roof exponentially, we're able to pack more and more capability into smaller and smaller packages, so that now my little 2-inch by half-inch by half-inch dongle here can can pick up signals from 2 megahertz up to, I believe it's 2 gigahertz. And whereas you guys know that when you've got an AM FM radio in a car, you have to switch between AM mode and FM mode, because the local oscillator can only cover either AM frequencies or FM frequencies, not both at the same time. But my little software dongle here is able to do that. And one of the things is that basically, I read a really good article recently about the history of software-defined radios. And what they pointed out was that as the technology has evolved, this A to D converter, the analog to digital converter, has moved closer and closer to the antenna. So once upon a time, it might have been after the digital mixer, or after the mixer, and just feeding into a digital signal processor. But now it's moved to the other side of the digital mixer. So you've basically got the antenna and then maybe a tuner or maybe a filter. And then that immediately gets converted into a digital signal, sent into a mixer with the digital local oscillator. And again, because you can pack so much, digital logic into a small space, this can cover a whole lot more frequency ranges. And I should also note that even though my particular system starts at 2 megahertz, I could buy, I think it's maybe another $20 for a module they call Ham It Up, and that could extend the range down into the hundreds of kilohertz. So if I wanted to communicate with hams on some of the much longer wavelength communication bands, that would be an easy addition to this system. So there's a lot of elements of mix and match or different ways to string things together to get the kind of capability that you want. And again, it's still all well within the realm of reasonable expenses. So I want to stop here because here's where I'm going to kick it over to sharing the actual software and showing what this actually looks like in practice. Over on the left here this is the little dongle that I was describing. It's just that 2 inches long. This particular one came with a nice antenna mount. I'm using it with right now with a collapsible telescoping antenna. That's the one here. It also came with a couple tuned antennas that are good at, one of them's 435 megahertz. I forget what the other one is. And basically, what I'm going to show visually is the capability of seeing what's in the FM band, what's in shortwave, and then what the kind of transient or intermittent emissions from something like a walkie-talkie end up looking like. So before I switch over to that, and with whatever problems might start to show up with audio, I'm planning to not share audio because I want to highlight sort of the visuals of the software, but I don't know if the audio is going to cause any problems. So before I take that big jump into unknown Zoom sharing land, does anybody have any questions about what I've talked about so far? Nope, everyone's falling asleep out there. I understand. Okay, so the software that I'm going to be using for this particular demonstration is free software. It's called Cubic SDR. And just like the number of different SDR dongles and SDR packages, there are a bunch of different SDR software packages out there. So I'm using Cubic SDR. My friend Ty Winkle, who's just a super ham and a super brilliant guy back at Ford, he uses SDR Sharp. And if you go out and either Google or look on YouTube, there's just a list as long as your arm of different options that, they each have their own strengths and weaknesses. Okay, so let's see how this works. So what I'm going to do right now, I've got this tuned to 105.1. But you can see some of the different FM stations that are local to me. Over here in the top left, I can choose my modulation. And I'm going to choose different ones over the course of the different demonstrations. But obviously for the first one, I'm just going to stick with FM. So AM is pretty self-explanatory. There's narrowband FM. For the ham radio community, we've got lower sideband, upper sideband, and double sideband. And then one nice feature is this has I&Q capability. I&Q is a way of capturing information that includes both the amplitude and phase of what you're looking at. So sometimes that is necessary to get a better sense of exactly what kind of signal that you're looking at. Okay, so I'm going to hit start. And I'm hoping that you're not hearing that audio, but I'm going to turn it down on my screen so that it doesn't completely mess me up. It's a little hard to talk over a radio ad. But I just want to highlight a few things that are interesting about this. So I can tune my center frequency to pretty much whatever I want within the operational range of my hardware. I can choose different bandwidths to look at. This up here in the upper right is really showing the modulation, because look what happens when I switch this to AM. All of a sudden it's just junk, and I can tell you on my side that the audio has changed to just complete static. So you can see when you're not demodulating it properly, this goes from being an intelligible signal of people talking to just noise. So with that, I can change from one station to another. And you can see this one's a lot more human voice talking, whereas the other one had a little bit more music, and you can kind of see the difference, a little bit of richer frequency content. And another thing that I really want to highlight is, again, the usefulness of this visual. So you've got this beautiful colored waterfall that's coming down at the bottom of the screen. And I mean, over here, they've got some units, minus 74 dB, minus 95 dB. But to me, more importantly, you know, nothing about this is precise, right? I would never try and take a plot like this or a spectrum like this and compare it to an FCC limit or a Sister 25 limit. That's really not what it's for. But it does really nicely show me that this station here, 104.3, is coming in a lot stronger than 105.1. And, you know, there might be kind of a ghost station far away over here at 105.5. There's some weaker stations over here. And the other thing that's really nice about this, take a look at the digital sidebands. So when FM radio went to being digital, they start to include these sidebands that have sort of metadata about the song that's playing, the station that's playing it, and that allows you on your car radio, you're driving along and you're not just listening to the music, but you can see the artist and the song title and the name of the station that's playing it. All that kind of information is included in these digital sidebands. And you can really see they look different in the waveform plot, right? So these are much more squared off. They're much more regular, very consistent amplitude. They look like a digital signal, whereas what's in the middle is a lot more variable. It's containing all that voice or music information. It looks a lot more chaotic, almost, you could say analog, you could say organic. But this gives you a sense of if you had an unknown noise source and it was interfering with something that you cared about, some device that you were interested in, you know, like what John and Candace were talking about with debugging, you know, the ESD effect on their computers. You know, obviously the troubleshooting they did for ESD was like perfect, but if it wasn't ESD, if it was something else in the environment, this could help you to determine where do I have a strong signal and what kind of signal is it? Is it persistent? Is it intermittent? Is it digital? Is it more analog? That's the kind of information that you can get from this kind of, you know, this kind of display and this kind of device. So I want to switch now. Actually, here's something that's a little depressing, because there's a really nice trick that you can do with these SDR radios, which is tune into air traffic control, because it turns out air traffic control is mostly just AM signals. And Ty used to do that all the time from his house in Canton, which was so close to the Detroit Metro Airport. And, you know, for plane enthusiasts, it's a lot of fun to be able to see all the different traffic that's going on at different times of day. Or for instance, you know, if the Blue Angels do a flyover, the air traffic control traffic, you know, audio traffic can get really interesting. Unfortunately, it turns out in Colorado, there are these things called hills and mountains. And I have not been able to get line of sight on Denver International Airport. So I went through the entire frequency set that's allocated over at Denver, and I was not able to get a single signal that I could lock onto. So that was a little bit disappointing to me. But what I can get is, if I go up to 162.5, so up in the short range, we go to narrow band, and then start my device again. Now again, this signal is pretty faint, but this is the NOAA weather station for Boulder. And I'm betting this, for one, this came in better at my house because I'm closer to Boulder at home. And for two, possibly the time of day is mattering, but It is a narrowband FM signal, and it did come through more clearly about 3 hours ago when I tested it. But again, so this is now operating on a shortwave system, which again, previously, if I had like my old hand cranked emergency radio that had AM, FM, and shortwave, but of course you need a different tuner for AM, a different tuner for FM, and a different tuner for shortwave because of the limitations of those local oscillators. Whereas now I can get all of that just with my little SDR.
Karen, this is Mark.
Okay, so
Karen.
one last one.
Karen.
So I'm going to move up to, I'm going to stick on narrowband. And now I'm going to take that walkie-talkie that I totally stole from my children. And when I turn it on, a couple of really interesting things happen. So up here, I go from having nothing but static to having a relatively moderate signal. And now, and it's not picking up my voice terribly well. I think because there's a bit of an antenna mismatch. But you can see it's narrowed down, or it's settled down into a pretty nice signal over here. But look what happens when I turn it off. It sends this kind of burst of energy across the spectrum. And when I turn it back on again, look at that pulse that it sends out when it turns on. It's really pretty amazing to see that the turn on and turn off transients all of a sudden spread its power along quite a wide bandwidth. Whereas once it gets to its steady state carrier signal, then it settles down a lot more nicely. But again, you can see from down here on the waterfall how things change as I turn this particular either noise source or intentional transmitter off and on. And for instance, like over here, there's something pulsing at a regular frequency. It's not me. That wasn't there 3 hours ago when I was testing this out. So that could be, an interference source that would be worth investigating. And again, when I turn mine back on, it shows up pretty strongly. Oh, I'm a little bit off frequency, that's why. So this is just, like I said, this is just an extremely simple demonstration of some of the capabilities of what an SDR, a low-cost SDR system can do for you. A couple of the limitations that I should point out: you can adjust the bandwidth, but only so much. For instance, when I was doing troubleshooting with the handheld spectrum analyzer back at Ford, I could easily set that to be showing me everything that it could pick up from, say, 30 megahertz to 300 megahertz and get a really comprehensive sense of what was around me. Here, the maximum bandwidth, I think, is 500 kilohertz. So you do have to do quite a bit more manual sweeping. And again, it's the difference between an $8,000 piece of equipment and a $30 piece of equipment. To an extent, you get what you pay for. But again, in terms of and I think we can all admit these kind of waterfall diagrams are just really pretty. So it's a great visualization. I know I've already enjoyed sort of showing my kids. It's like, look, this is what it looks like when music is playing on the radio or when we're playing with our walkie-talkies. Like, there's real stuff out there that you can see. So it's good for an informational standpoint. It's good for a very high level, rough and dirty troubleshooting standpoint, and also for educational purposes. This is the kind of thing that you can take to a school or take anywhere, right? Because I've got this plugged into my laptop. I can just walk around with it and show people what's out there. You can listen into other people's ham radio conversations. Some people have been using these to decode pager signals. I don't necessarily recommend that one. I feel like that's getting ethically squidgy, but there are people out there doing that. And yeah, so basically I just wanted to introduce this as a potential, new tool in the toolkit for anybody who's interested in exactly these kind of phenomena. So with that, I think that is most of the material I wanted to cover. So how about I kick this back? I will stop sharing for the moment. And I think the idea is that we'd open the floor to questions from everybody after this, right?
Yeah, that'd be great. Can you hear us, Karen?
Yeah, I'm turning my volume back up so I can hear you.
Okay, great. Because I had a real quick question. I noticed on the FM band, it looked like it might be HD radio on that FM, two of the FM stations.
Exactly.
Yeah.
Is there a decoder for HD radio for these software-defined radios?
Yeah.
This is Neil.
Hey, Neil.
I've been running demos. I did it in my makers class last week. There's an open source project called NRSC5. I'll paste it into the chat.
Okay.
I have it running on a Mac and a Raspberry Pi.
Okay, that'd be very interesting.
It is pretty neat. It allows you to pick the different streams. We have a station on a mountain that literally I'm in the shadow of. And they have 3 digital streams running. So I can pick out the different digital streams and get the data out of them. There is so much you can do with those dongles.
Yeah.
I also, our local club here, we're working on parsing data that we're getting from our weather stations, which just use very simple open text transmitting. And by playing with the same utility, I'm picking up tire sensors, power meters, the kilowatt hour meters, all sorts of things. It's all out there for analysis and to grab. And I just wanted to add one more thing. There is a new product that one of my students last night introduced me to, and I can't believe I didn't know about this. We've all been playing with these things called nano VNAs. It's a little $50 vector network analyzer. They've done a spectrum analyzer on the same platform, and they're $50.
I own both. In fact, I have the newer version of the Nano VNA, the one that comes in the metal case. It's version 2. It goes all the way up to 3 gigahertz. Quite nice.
I'll put the link for the Tiny SA at RNL. That's the official version.
Okay, great. Any more
Neat
questions? I saw Mark was trying to break in with a question. Mark Stefka.
Yeah, Karen. When you were looking at the weather station, one of the interesting things that you can do is actually duplicate slope detection. And I know there are probably a few folks that are familiar. Karen, are you familiar with slope detection?
Only a little bit.
Yeah. Okay. I just wonder if you had tried any of that to see how good the this dongle was at that.
No, I haven't had a chance to play with it with this system yet. I actually had to rebuy this because the one I had back in Michigan got packed and is somewhere in my garage in a box, who knows where. So,
okay.
But no, yeah, there's so much more you can do. You can do, and max hold, max hold to survey what's around, averaging the, I'm really just scratching the surface of this one.
Yep. Okay. It's also interesting to go to the AM detector for a narrow band FM. AM is kind of replicated by narrow band FM, and so that's interesting too.
Mm-hmm.
Okay.
More questions for Karen?
Or for Mark, or for John and Candace.
Yeah, sure.
I know we kind of slammed from one to the other. So. Actually, I have to admit, I had a question for John.
Okay.
One thing I wasn't clear about, why did the balloon pop in that one video? If John's still online.
Candace was saying they were having computer problems, so I'm not sure.
Oh, bummer. I see him on, but he's still muted. He might be
I see him on
debugging.
mute. I don't know. I guess
Okay, yeah, 'cause I missed that part.
So I recorded this session, hopefully, and if anybody would like.
Can you hear me?
Record
I'm
it.
here.
Yeah,
I'm back.
go ahead.
I had to get my audio. Sorry, the balloon pop was an example of.
Nope, gone again.
We lost you, John.
The balloon pop? Yeah, the balloon pop was done with a resistor.
I see.
So we turned, instead of the LED,
Oh,
I turned on
okay.
a resistor and it
Cool.
popped the balloon.
Okay.
Gotcha.
Stan Wagner, if you can hear me.
Yes, go ahead, Ben.
I was wondering, what was the dongle you used for your demo?
Oh, for my demo, it's an NESDR Smart, and I got it from the company Newelec. I can put that in the chat.
Okay, yeah, thank you.
Those are pretty good.
It's worked very well for me so far.
Yeah, the two best dongles are the lower price dongles are that one and the RTL SDR blog dongle.
Which I think Scott was saying he just got.
Yeah.
Yeah, I just got one. It's still in the wrapper, but mine is the RTL SDR. That's the one I got. But haven't got a chance.
That's actually one of the better ones as far as the cheap ones.
Right.
Yeah, it's just a toy at this point.
Oh, and I see a question from, what are the major differences from Cubic SDR and the other options? I think a lot of it has to do with the user interface, which ones you just happen to like best, but also whether or not they're optimized for the ham radio community. That's my impression, but again, I haven't had a chance to play around with a lot of the different software packages. I've been focused on the Cubic SDR. Neil might have more.
Well,
Cubic seems to be the most feature-rich of the ones I use. On the Windows platform, you have some other options, especially if you get into things like the RSP1A from, trying to think of the name of the company now.
oh, SDR Play.
SDR Play. Their software is based on a company that they bought. Their Windows software is excellent. They're porting it to Linux and Mac right now, but they recommend Cubic for the Linux and Mac users pretty much. So that's their recommendation. SDR Sharp has a lot of really neat plugins, so you can do a lot of playing with it. And unfortunately on a Mac, the closest thing to that is going to be called GQRX, which isn't bad. But they're all decent. Some of them are easier to do direct sampling on compared to others, which is a neat feature that some of these dongles have that lets you go down below 30 megahertz. Cubic is also good for that. So it's a little complex, but there are worse.
And again, you can find a lot of YouTube reviews out there that'll do side by side of different software packages, different different dongles and their capabilities and what's good and strengths and weaknesses for each.
So does most of the software work with most of the hardware?
Yes, they really do try as much as possible to be pretty agnostic between software and hardware. I mean, I'm sure it's not perfect, but I have yet to encounter a major driver conflict where a particular, at least any of the popular dongles wouldn't work on most of the popular software.
Okay, that's really good.
Yeah.
I would concur with that.
Okay, great. Anybody got anything else? Okay, I'd like to thank all you folks for attending this evening, and I'd also like to thank all of our speakers tonight for all their preparation and presentations. I know I got a lot of it. I hope you guys did too. And watch for your emails as we will send out the announcement for the next meeting. And everyone have a good evening.
Great, thanks everyone.
Thank you.
Thank you, everyone.
Give my best to everyone at Ford.
No, I would
Thank you all.
complain that you gave me your job, Karen.
Oh.